A very interesting application of the chi-square goodness of fit test is in accounting with this law called Benford's law. It seems like a really strange law at first, and it's kind of amazing that it holds so reliably. So this Frank Benford in the 30s discovered from looking at lots of valid records that the first digit in valid numeric records tends to follow the pattern that we see here in table 717. What this really tells us is that we mostly see ones as first digits, right? We're going to see ones as first digits much more often than we're going to see any other number, well, any individual other number, with 9 as the least frequent. So they go down in frequency as you go across. As I try to understand why this would be true, what I think about is anytime you're getting into the next number of decimal places, say you're going up from tens of thousands to hundreds of thousands, you have to start with 1, right? So you have to, if you imagine that your income is growing or your expenses are growing or something, before you get into the 20s of thousands, you're going to go through the tens of thousands. So I imagine it that way, that as these numbers grow, they always go through the 1s first and then the 2s and the 3s before they get up to the values with a higher digit. So I don't know how valid that is, but that's the way I think about how this could be true. So what we're going to look at is a data set that consists of 7,273 invoices. And we're going to look at these invoices and see if the numbers tend to follow Benford's law. If they don't, then that could be a flag, a little bit of a red flag like the IRS might use for potential fraud, that the IRS might then look a little bit more closely at this tax return or at this information that was submitted. So our null hypothesis is that the invoices do follow Benford's law, that we don't see major deviations from that first digit rule. And our alternative hypothesis is that somehow they differ from Benford's law, that we see enough deviation from this that Benford's law is not all in all followed. We're going to look at the data set Benford and with the variable invoices, but note that in StatKey, this is actually in the drop-down menu. So this is in the drop-down data menu. And the nice thing about taking it from the drop-down data menu instead of uploading the file is that the null hypothesis is also already written in for us. So we're going to StatKey now. We're going to choose chi-square goodness of fit. And from this drop-down menu, I'm going to choose Benford invoices. Notice that there are 2 different Benford files here. There's an address digits file, and that shows up in a homework assignment, and there's this invoices file. So the one in your homework assignment is not the exact same one that we do in this example here. We have the counts over here, and we can see if we click on null hypothesis that instead of the default being that they're all equal, Benford's law is already written in here. If we were to upload the file, we would have to enter these manually because this is our null hypothesis. The null hypothesis comes from the Benford's law. The data comes from the actual file. So here we're going to, yes, we did look at that and verify that it's the same. The correct degrees of freedom for this chi-square distribution, we have 9 categories, and n-1 or k-1, number of categories minus 1, is how we get our degrees of freedom. So we want a chi-square distribution with 8 degrees of freedom. And let's go ahead and, while we're here, also write down that chi-square test statistic of 27.022. So here is a curve with the correct degrees of freedom. And on this, we're going to locate 27.022. We can see these are spaced by 5. This would be 25, and this would be about 30. So my 27 is right about here. If it's off the graph, we know that that's a really, really small p-value. So we're shading in a tail that's right about there. Our p-value is very small. We can say it's very close to 0. I'm only going to be this vague if it's all the way off the chart. I would not call 0.02 close to 0. Close to 0 is like it's probably 0.00 something, right? Close enough to 0 that we don't really care to estimate it anymore. And we'll go into StatKey now and see what their calculation of that p-value is. So coming back to the main page, theoretical distributions chi-square, 8 degrees of freedom, right tail, 27.022, and we get a p-value of 0.0007. So sure enough, very small. What this p-value tells us is that we do reject the null hypothesis that these follow Benford's law. They in fact seem to deviate quite a bit from Benford's law. So we do reject the null hypothesis. We have overwhelming or very strong evidence that they don't follow Benford's law. So part 1 of my conclusion is just based on the p-value. Generally, if we get statistically significant evidence, we include a part 2. We're only asked for part 1 in this case because the nature of this question makes it to where perhaps part 2 isn't that interesting, right? If they don't follow Benford's law, you're probably going to get audited. And do we really care whether we didn't follow Benford's law because there were too many 5s in the place of that first digit or something like that? Maybe not. Or because there were too few 8s or something, right? It's not as interesting a part 2 in this case as it is in most cases. So most of the time, by default, we give both parts if we reject the null hypothesis. But in a case like this, if we're only specifically asked for part 1, there's probably a reason why part 2 isn't particularly of interest in this context.